Welcome to the discussion on the concept of strain. Is also the part of strength of material one course. In particular, this particular topic belongs to stresses and strain chapter. We are going to see in the discussion, we are going to see what is strain, how the strain is developed, how the strain is classified, and also we are going to look upon the topic of stress strain curve of a mild steel. So by the end of the discussion, I am sure the learners will be able to understand the difference between the normal and shear strains, the uniaxial tensile test conduction, as well as the salient features that we are going to observe on the stress strain curve of mild steel. Also, what is Poisson's ratio and what is its significance? So let's start. Look at the first one. The development of the strain as well as its measurement and its types. We have already gone through this kind of discussion when the concept of stress is discussed. Here you can see a cylinder was unloaded in the beginning. Later on an external load is applied on the cylinder in any one of these forms can be applied. It can be a tensile load, or it can be a compressive load, or it can be a bending type of load, or it may be a shear type of load applied, or it may be a twisting kind of loading, a torsional moment applied, or maybe a combined loading, which means a combination of any of these loadings. Now, the external load is what is actually causing the deformation of the body, which was applied in any one of these forms. That leads to the deformation of the body. In the process, the intermolecular attractive forces opposition is what causing the development of the stress that we discussed in the stress concept. Now, whatever the deformation happened, the ratio of that particular, these deformation generally they are very small, very small. Sometimes you will not be able to see these deformations, but we can, of course, through the strain gauge measurements and all, we can at least identify this, that there is a deformation happened. The ratio of that particular deformation, however small it may be, the ratio of that deformation, right, the ratio of that deformation to the original dimension of the body, right, the changes in dimension to the original dimension. Okay, in other words, the deformation also called change in the dimension of the body to the original dimension. Okay, that particular ratio, right, the original dimension can be taken in any one of the any one of the three axis directions, maybe x or y or z, I mean to say length or breadth or height direction. Okay, any direction you can say, whatever the deformation undergoing in that direction divided by the the original dimension. That's how the strain we define, right? Next, how the strain is classified. If you look at the classification of the strain, it was mainly classified into normal strain and shear strain. And let's see one by one. What is this normal strain, right? How do you measure it? Okay. So first of all, normal strain, either it is normal strain or shear strain, we have already discussed. Without external force, there is no question of development of the stress or strain. Now, if that forces are acting on the body, right? So caused by the forces, normal strain is caused by the forces, right? What type of forces? When these forces are acting in a direction normal to the right cross sectional area of the material, normal or perpendicular to the cross sectional area, right? So basically we are defining normal strain. Okay, it is caused by the forces acting in a direction perpendicular to the cross sectional area. Then how do you measure it? For example, this is the cross section, right? This is the cross section, maybe a circular cross section here, right? This circular cross section before applying load, this was the position. Let's say this is a plane. Okay, a plane cross sectional area. Here we are having now after application of the force, it has been deformed here, right? So it took a new position here. Now the relative perpendicular moment of one reference plane with respect to another. So that this relative moment from here to here, right? That deformation, whatever, that's we are going to measure and divide by the total or original dimension of that is what we are calling as normal strain. That's how we measure it. Just like stresses are both compressive and tensile, similarly of the strains also. There is there is a strain gauge used for the measurement of the strain, right? This strain gain was attached to the test specimen which you are going to for which you are going to measure the strain. This is attached, and the electrical potential difference which is measured through these leads before applying load and after applying load is what gives the deformation. Okay. Now the other kind of strain, namely shear strain, they are also caused by the forces, right? But what type of forces? When those forces are acting parallel to and lie in the planes of the cross section area. So it's just quite opposite. Previous one, they are caused by the forces in a direction which are acting in a direction perpendicular to the cross section area, whereas here these forces are acting parallel, right, to the areas, right? Now, how do you measure this, right? The relative displacements that are measured parallel to reference planes, right? If this is the original, let's say this is one plane, so because of the shear, generally shear leads to distortion. We previously discussed it, and the shear stress causes distortion of the object. Now this relative displacement, whatever here, this we will call it as shear strain, right? So now the normal strain or longest strain or direct strain, all this, all are same. If a body, let's say there is a cylinder, is subjected to some external load P, okay, as we are seeing here, right? In the case of a rectangular bar, whatever deformation happened in the length direction, say delta L divided by the original cross sectional area is what is called strain, right? Of course here why it is called particularly normal strain, because this is the cross sectional area acting, the load was acting perpendicular to this particular circular cross sectional area, or in case here a rectangular cross sectional area. Okay, and of course it is well known, once it is a ratio, then it has no units, right? Now the measurement of the shear strain, if you look at here, here is a rectangular block, you are seeing a square block here situated, and it is subjected to some kind of shear stress, right? Then how do you calculate the shear strain? So what we will do here is the angle, the tangent of the angle through which the two adjacent sides, any two adjacent sides you can take, right? What is the angle that has been undergone? The tangent of the angle, a tan of the angle can be taken as the summation of the any two adjacent sides undergone. Let's say this side and this side. Initially, this is the shape. This side and this side undergone after the application of the shear stress. That's what we are calling as a shear strain. Because the angles are very small, sine and tan, both you can take an angle itself, right? So that's why, although it is tan gamma, we will say simply gamma undergone by the two adjacent sides AOB and A dash O dash B, which is before the application of the load and after the application of the shear load or shear stress. Now that's gamma is what angle AOB minus angle A dash OB dash, right? So this 5 by 2 plus 5 by 2 together give the shear strain value. Now we come to the second part of the topic, that is the normal stress strain curve of the mild steel, right? This test was basically conducted in universal testing machine, and for that was we have to prepare a specimen, right? This is basically a static type of test. That test is conducted on any one of these specimen. One can take a rectangular specimen cross sectional area or a circular cross sectional area specimen you can take. The specimen has to be made in this form. If this is the length of the specimen, we have to keep some grip, because the specimen has to be held in the machine, so some grip is left on either side, and in between there is a length kept separately for the measurement of the calculations. That length what we are calling as the gauge length. For all practical purposes of length, we will take this gauge length. Length of the specimen which we want to determine the mechanical properties. That's what this gauge length is all about. And once you have marked the specimen like this, with what is the gauge length of that and how much projection you are left for gripping purposes. Once you have made it, then your specimen is ready for testing. This is the machine, universal testing machine. Of course, this is an old type. This is a schematic diagram, and a machine of somewhat in the Middle Ages, recent times. You can take this kind of, of course now sophisticated ATMs are also came, but anyway, this serves the purpose for for understanding. So this uniaxial tensile, uniaxial tensile machine, that universal testing machine, the specimen here, there are two compartments. There is upper compartment and the lower compartment. The upper compartment is used for conducting the tensile test, whereas the lower compartment is used for the compression testings, right? Specimen compression testing, whereas the specimen tensile tests are carried out here. And there are two crossheads, the upper crosshead and lower crosshead. One was a movable one, another one is a immovable one. And basically the specimen is inserted for tensile test we are doing. The specimen is gripped in between these upper jaw and lower jaw. The upper jaw usually it is fixed, and the lower is jaw, it moves up and down. As a result, the load is applied. So if it goes down, usually tensile load is applied, right? And as far as the loading concerned and the recordings are concerned, there are two units. One unit is, so here these are the steps. First you have to grip the specimen, you have to securely place the specimen between these gripping points, the upper jaw and lower jaw. Thereafter you will be able to see there is a unit for the application of the load. You can increasingly apply the load through rising of the pressure in hydraulic oil, and there will be some unit for recording the deformations that are happening, or the stresses that are happening, that you can record it, right? So one unit is there for applying load, and another unit is there for the how much stress is developed in the specimen, or how much deformation the material is undergoing, right? That you can note here. There is a recording device in the form of a computer or some kind of CPU available system. You can measure these things, how much load is applied as well as how much deformations or stress developing in the specimen. Now, the stress and you can plot here from, as we told, from the two different units that you are from the one unit you can see how much load applied on the material, on the other unit you can measure the displacement. If you plot it, this is how you will go and get, right? Most likely or most commonly we are going to draw, rather than load and displacement curve, usually you draw stress and strain curve, stress and y-axis and strain on x-axis, right? So this is the more common diagram. Now here there is sometimes another similar stress strain diagram is that is called true stress strain diagram rather than conventional stress strain diagram. The difference is that in one case, that is the nominal or conventional stress strain diagram, what we will do is for all calculations, whatever stresses at any instant you are calculating, for all those purposes you are going to take the original area of the specimen which was measured before putting the specimen into the universal testing machine. Whereas if you want to know exactly precisely measure how much amount of stress that was developing in the specimen, right, for that purpose you are going to take the area of the specimen at the point of or at the instant of the load application, right? If you take that actual area during the actual area when the load was applied, that instant if you take what is actual area available, actual area is keep reducing, right? When you stress the specimen and tensile load is applied on the specimen, your specimen area will be gradually reducing. So gradually the area reduces, then it changes. So if you take at a particular, let's say x amount of load, say 100 newtons is applied, at that point there is some reduction in the area. If that take that area and divide the load with that particular area available at that time, you are going to get the exact stress, true stress in the material. If you plot all those stress values, you are going to get a true stress strain diagram, right? Of course, now our present discussion is limited to this conventional stress strain diagram presently. So let's look at that. The stress and strain, if you take like this and if you plot the values you are going to obtain like this, this is the general trend comes for a mild steel case. You are going to get this. So you are going to see some of the salient features or salient points that you can note here. This is the trend going. So there are 5 or 6 major points that you are supposed to identify for our understanding, a clear understanding of this diagram. So those points are, of course, this is the origin, stress taken on y-axis and strain taken on x-axis. Now these points, salient points A, B, C, D, E, F, G. Let us try to know what is this. So the point A here, up to the point A, you can see this is almost a straight line, which means the stress and strain both are proportional to each other. Not only elastic, but also is proportional. Stress is proportional to the. So that particular point A is called proportional limit, okay, or limit of proportionality. Till the point A, the stress and strain both are proportional to each other, right, as well as, of course, elastic. But the elastic nature will continue up to the point B, but the proportionality will be there up to A. In other words, after crossing the point A, the stress may not be proportional to strain, but still it is elastic, right? So, but beyond point B, the material does not recover its deformation if you remove the load. That's why the point B, up to the point B, the elastic property of the material holds good, right? So there was a famous law in this contest of the proportionality and the proportionality limit contest. because up to that point A we told that stress and strain are proportional to each other. If you take that proportionality and replace the proportionality with a constant, you are going to get a constant called Young's modulus of velocity, and this particular law of stress strain proportional each other is called Hooke's law, right? So that if you substitute the basic formulation for elastic modulus, you are going to for strain you are going to get this kind of formulation. Sigma is proportional to epsilon replaced by a proportionality constant E called Young's modulus. You are going to get sigma equal to E epsilon, and of course you can resubstitute for stress load by area and as well as strain delta L by L. Just now we discussed this deformation by the original line that leads to the this kind of formulation. PL by A delta equal to PL by delta L is equal to is a linear relation between a sigma and strain, right? Now, as just now told that beyond point A, still material behaves elastically up to the point B, and that point B is what is called your elastic limit. Now point C and D, in other words, we just crossed the elastic limit. After that, the material no more stays in elastic mode. The material starts permanently deforming. So that permanent deformations occur after. In other words, when you remove the load after the point C and D, the material, whatever strain, it cannot come back to the original position. The strains are not recoverable, right? So the permanent deformation happens. So at that point, the loads, those points are called C and D are called the yield points, right? Now this for design purposes, we will be generally using the lower yield points, right? Then if you go still further, right? If you go beyond that point C and D, a further increase in the load will cause marked deformation of the whole volume of the metal. The maximum load at which the specimen withstand without failure is called ultimate strength. So you are going to see here the maximum load that can take, right? Not E here, actually F, right? So it's you can see there was after point we are discussing about E, right? Further increasing the load will cause marked deformation of the whole volume of the metal. The maximum load at which the specimen withstand failure without failure is called ultimate. That's point F what we are saying, right? That point is called F is called the ultimate strength, right? Here in the point E, there was one particular observation we can make. At the point E, the specimen is going to form this kind of the highest point E on the diagram corresponding to the, this is actually F actually, not E. So F the diagram corresponding to the ultimate strength of the material. As you are seeing, the highest point is a F. Is a typographical error actually. What happens is after that point E, let's say this continues actually. Point F, the bar begins to form a neck, right? So it forms a neck here, right? And then the material, the load failing from the maximum until fracture. So the last point we can call it as, right, is called the failure point. What you are seeing actually it was represented as G, right, in this case, but actually it is F. Okay, I will change for the sake of readers. This one here we are calling as F. There was no such significance for the point E as such in our discussion. Okay, and the final point, the failure point, is, in our case, it is the failure point is G, right? Okay, so this is about the salient features of that particular stress strain diagram. So the finally the failure occurs at the point G. Okay, so this is about the stress strain diagram and its features. Now let's come to the last topic, right? That is the Poisson's ratio. Now, if you take a particular rectangular object or any bar you are taking, apply load in one of the directions, say longitudinal direction. What happens? We will be observing this. Not only the stretching of the member takes place in the direction in which the load is applied, but also in other directions, you are going to get a lateral strain. In the sense, you are going to get a compression of the body in the other direction. Right? So contraction happens in the two direction, elongation happens in the direction which your load is applied. Right? So this effect is what is called Poisson's effect, where in one of the direction the uh, material is subjected to one kind of deformation, other two directions it is exactly opposite. Suppose if it is compression, the other two directions will be stretched out. Okay, that effect is called Poisson's effect. Now, as the material elongates in x direction, now if you take any direction, say x direction you are taking, it also contracts in the two other directions, like namely y and z directions, right? Now, how do you define this Poisson's ratio? The ratio between the lateral strain. What is lateral strain? The strain happening in the other directions, except the longitudinal direction. The other direction, whatever the strain happens, that is lateral strain. That lateral strain divided by, or you can say that the ratio of the lateral strain to the longitudinal strain, right, is called Poisson's ratio. The Because the mutually opposite effect is happening, the negative is used, negative sign is used here. So because one direction is stretched out, the other direction is having quite opposite, therefore the negative is used. So since the axial or lateral strains are opposite, then the negative sign is used. That's what I just told. And then the lateral strain, if you want to calculate, you can calculate using the the help of the strain in the longitudinal direction. You simply multiply with the negative of the Poisson's ratio. Now, if you look at the Poisson's ratio for the different materials, usually it varies between 0 to 0.5. For most of the metals, it lies in between 0.25 to 0.35. And for concrete, all those materials, it is between zero point 0.1 to 0.2, like that. So, of course, the highest value is for the rubber. So that's the whole discussion. The summary, you can just look at it for retaining ourselves information. We have defined the strain, right, as the ratio of the deformation to the original dimension, which was basically caused from the externally applied forces, okay, in the process of resisting the deformation caused, right. Stress develops, of course. The strain and stress both are happening simultaneously, and this strain is divided into two types, primarily say normal and shear strain. When the applied force is in the direction perpendicular to the cross sectional area, we will call it as normal strain. Otherwise, if it is parallel, we will call shear strain. And this is how it will get measured, the deformation by original length, right. For same as in the case of shear strain, we are going to take the angle, the relative angle of a particular plane, or the tangent of the angle. And these are about the discussion about the stress strain diagram and salient features, right. We majorly discussed about the point, say A. Point A is called the proportionality limit, B is elastic limit, because up to the point A we have the stress strain proportionality exists. Beyond that there is no proportionality, but the elasticity property still prevails up to point B. So point B is called elastic limit. Beyond that, there is no more elasticity, and the material starts yielding, which means permanent deformations will set in, and material cannot be recovered. And the 2 points called C and D are upper and lower yield point. For all design purposes, we'll be using lower yield points. And the other important point is the maximum strain happens, right? This portion is also called no, what you call strain hardening stage. And this particular topmost point where the maximum strain that can be taken, or stress can be withstand by the material without failure, is called ultimate strength. And of course, the finally wherever the failure happens, that point is called fracture point or breaking point. So that's all the discussion, and you can refer this material mentioned here. Thank you very much.